Okay, um, let's start. Again, thank you very much for coming. Welcome. And what is the task today? If you kind of forget what we had about sheaves, pre-sheaves, etc., that is just very okay because today I don't need them. The only thing that you need today, I hope, is that the definition of topos that you remember. One. Two, you remember that we had the first construction of toposes via this construction of sets to the C or C opposite, if you like, and some sort of refinement, say, via sheaves that I don't want their construction, but the only thing is that we had the first construction kind of completed. And today I want to talk about the second one. The second one is kind of better for our purpose simply because they are motivated more logically than, say, more geometrically. So that's probably good because we are, I guess, more logicians. One, two, they are more logical, therefore they are closer to logic, therefore they should be easier to use for independence, right? Which is our goal. So, and they are called a, let's say, Heyting-valued sets. So this is our task today. So the general idea is this. So more or less, we know that any topos is just some sort of a word of sets, right? And here we construct a new notion of set via varying a set over some category of time, if you like. Here the idea is different. So I want to work with sets, just the usual sets, if you like. But then I want to change the notion of truth, the notion of truth value. Because whatever we say about things, somehow based on some notion of truth value, right? If you change it, probably you change the whole discourse. So what do I mean by that? Let's say that you have a set A, right? This is just the usual set. So there are some basic things that you can say about the set A. The very basic two things are that something is in A and two things in A are equal, right? So the first thing that I want to do is just to change the truth value of these guys. In the usual classical theory, I would say that the truth value is either 0 or 1. It's either true or false. But now I want to assign some sort of extended truth value of it, not in 0, 1, which is just the usual poset, but in some Heyting algebra H, right? So therefore, the first thing that we have to do is just what is our new notion of values, right? Before doing any set theory, I need a fixed notion of a truth value. And how to model that, I would say that let's just pick a complete Heyting algebra. So do you remember what a Heyting algebra is? No. So I have to recall it. But that's not that hard. So the thing is that you have some, say, H. It's a set, some order, therefore it's a poset, with the following structure. One, you have the top element, say, meaning that there exists some element, 1, such that for any A is less than 1. You have a finite, or let's say binary meets, meaning that any two elements, A and B, inside H, you have the greatest lower bound. So you have something that's called A, B, A conjunction B, A meet B, which is less than A, less than B, and it is the greatest with that property. You have the dual of these two. You have the bottom element, meaning you have 0, and for any A, 0 is less than A. What else? You have finite joins. But okay, let me define it. So this is the definition of a Heyting algebra. And finite join simply is just you have A, B, or let's say binary join, why not? And this is just some upper bound of both of them, but the least possible upper bound. And the last guy is implication, Heyting implication. So it's just some binary operator with the following property that for any C, C is less than A implies B if and only if C and A is less than B. So any lattice, any say poset with these structures is called a Heyting algebra. And the Heyting algebra is complete Heyting algebra is complete if any set, say S, any subset of H has the least upper bound that we can denote by this least upper bound by this guy, or if you like, by this. So A is in S. So this is kind of the generalization of the binary joins to arbitrary join.
So there's no negation.
There is no negation, but you have implication.
Negation sort of symmetric.
No. No. Just this one. The other one is called co-implication, which is just something else. So you have just this implication, and that's a good thing to say that usually people write negation of A as A implies 0. So you have it. Okay. So one thing that I have to say about the complete Heyting algebra is that when a Heyting algebra is complete, when you have all the joins, it is easy to prove that you have also all the meets, right? So then for any set, also I have the greatest lower bound also. Okay.
So is that in this fake negation?
Yes. Yes. That fake negation is intuitionistic negation. So it's not that fake. But anyway, this negation is fake because it has one half of the property that we want, right? It has this property. So these two guys equals and also less than 0, if you like. Let's say equals 0, right? That is the thing that something and its negation cannot happen at the same time. But classically, we also have this guy that A or negation of A is true, but this is not necessarily true in Heyting algebras. So more or less, this is the difference between Boolean algebra and a Heyting algebra. Therefore, definition, Heyting algebra, H is called Boolean if A or negation A is 1 for any A in H. Yes, always we have it. Whenever we have Heyting implication, infinite. We have this one. That's a very good question. So we have this in any complete. So first, complete Heyting algebra. That's the notation. H is say distributive or infinitary distributive, or it's a local in the following sense that A or no, sorry, A conjunction this guy equals to this. One, no, it's a property of any complete Heyting algebra. One, two. Of course, then if you have finite joins, you also have this. But then that one is dual, that distributivity is dual, meaning that if you have that, then also you can change just conjunction and disjunction with each other, and you also have it, meaning that you also have this if it is important. But this is finite. Say, this is the second thing, and you don't have it for infinite conjunctions, right? And that equality is just a very easy consequence of the existence of Heyting implication, if you like. So, second question. Yes. The negation of the middle element is itself, I guess. No. That's a good question. So what is the negation of the middle element? It should be 0, I guess. I guess. Because with the conjunction it should goes to 0, so it should be 0. Okay, so okay, you may say first, you may say that God, this is just so abstract. What do you do there? So it is not that hard. So let's say that you want some sort of notion of truth value, right? To formalize your weird mathematics, your alternative mathematics. Please. So first, of course, you need some set of new truth values. Two, you need some order, and that order is just implication, right? Something implies something else between your truth values. We have also the same for 0 and 1, right? 0 is less than 1. So meaning that if something is false, then so 0 implies 1, right? And so this simply means that you have 1, you have the top element, you have always true, you have always false. Where are you, right? And you have binary meet and join. Simply you have conjunction and disjunction. And this definition of least upper bound, or I don't know, greatest lower bound, it is just simply the definition of being conjunction and disjunction in the usual sense. So if you think about it, simply when I say that A and B is just the least greatest lower bound, I say this, I say that, this is that the guy is lower bound. And also I say that for any other lower bound, it is less than A and B. So these are just the two obvious rules that we have for conjunction, right? So the same for disjunction. So simply I'm saying very algebraically that I have conjunction and disjunction. This is kind of different. I'm saying that I have intuitionistic implication, but not classical. Intuitionistic implication is this, right? So with the same idea, you would say that you have, if you have implication, you have this. This is modus ponens. If you have A and A implies B, then you get B. And also you have this kind of deduction theorem that C and A, if they implies B, then C implies A implies B, or it is just the introduction of implication, right? The difference is that in classical setting, you also have this, or equivalently, you have this, right? Which is not necessarily true for our negation or implication. But sometimes it is true, and then we call it Boolean algebra, right? So simply I'm saying that I have all the usual things that we have in logic, but in diffusionistic. However, there is also something else. I have that infinitary thing. Where are you? Yes. I have this infinitary thing, right? Which is kind of unusual. So let me hate him. So you have this, and we don't have these type of things in logic usually, right? Because they are infinitary. And also this guy. Yes, we don't have it, and I need it to simply interpret quantifiers, as we will see later, right? So it is just big existence over some infinitary set, and this is just universal quantifier over some infinite set. So this is my trick to do, right? So this is just a very basic thing that I need, and you may say that, okay, we need some examples of these guys. The real examples that we use are the following. So first, let's say that you have some poset, right? Any poset, and then define your H as offsets of P, and the order is just inclusion. So offset means just a set that's closed upward, right? So you think like this, right? So this set, for instance, is offset, but this set is not offset, right? So these offset guys, with the order is just a Heyting algebra. Of course, you have empty, offset, the whole thing, blah blah, union, intersection. But also maybe that's good to see the implication. The Heyting implication is simply the set of all x's in P, such that for any y bigger than x, if y is in U, then y is in V. So this is just the usual Kirk style Heyting implication, right? Uh-huh.
So it's completely determined by the conjunction.
Exactly.
But to add it to a model with an object, you need this C to have some kind of upper bound, this set of C's.
Yes,
So
that's a good thing to ask. Let me say like this. So let's say that we live in a world that we have a poset, say A, and we have conjunction, we have disjunction, we have 0, 1. And is it possible to define implication? Of course, implication is uniquely determined by that condition, right? So you cannot define two different Heyting implications. But is it possible to construct the Heyting implication? As Neil suggests, so it is kind of obvious, right? So you have to define this as the big. So therefore, first I need this infinitary joins. That's good. But then if you define this, you have half the property, not the other half, right? So if you have this, then you have that. But also you have to come back, right? If you try to prove to come back, then you see that you need another thing. And another thing is this distributivity.
This least upper bound complete condition, would that give you this?
No, it allows me to define this, but then that guy should have the property of implication. One half of it is just based on the definition. The other half, if you want to prove it, yes, then you need this guy. So therefore, you need to have any disjunction and that distributivity. If you have it, then you have your implication. And if you have your implication, you have this distributivity, Yeah, both assuming that you have all the disjunctions, right? So then you can define. And actually, that's a good thing to do, because if you open up this definition, you see that actually I'm doing the same here. So this is kind of weird, but it is just the union of all offsets such that the intersection with U is a subset of V. That is just the spell out version of that. Yes. Yes. As long as you have any join, right? Yes. Then yes. Okay, right? So one example is just this key style models, if you have seen them. Otherwise, you can think of just a post-it. And the intuition of the offsets are that, so these guys are points of time, and something is changing over time, right? And if you, and it is offset simply because if you prove something, then it remains proved in the future. Therefore, the value of a proposition is just some offset, right? So then I have to use offsets as the values of propositions, the points where the guy is true, right? Or proved. And then the implication would be some implication is true at some point. If whenever in the future the guy becomes A becomes true, then B also becomes true, right? Because you proved your implication here, it remains proved, and therefore in the future, if you have A, you can just plug it in and then use to have B. So that is different from the usual classical implication, which says that something is A plus B is true at one node if either A is false or B is true. That's different. So the second example is the very obvious. Okay, no, maybe that's better. So X is a topological space, and then as we had before, so O of X opens with this guy is just a poset, which is a Heyting algebra. We saw it, of course, we have all the unions, blah, blah. Both of them are complete Heyting algebras. But then implication maybe is not that trivial, and we had it before, so it is just the interior of the classical implication. And so that guy is some specific example of this guy, simply because all the offset of something is just topology. And the last one is some specific example of this, probably. So let's say that X is a set, not a topological space, and then you can, okay, why not? You can all the power set, right? All the subsets with the intersection. It is also a Heyting algebra, but now this time it's a Boolean algebra, right? Because everything has just a complement. There is some intuition about this that I said, the intuition of time. There is also an intuition about this example. The intuition simply says that X is the set of states of, say, some machine or something, and then so a proposition, which is just an open here, a proposition is something that it's just a subset of states, and some state have the property. If the state has the property, then we can prove it or verify it, if you like, in finite time. Right? We cannot decide it, but we can verify it in finite time. So one example helps. The example of the usual R with its topology. Then think about this guy, which is open, right? Right. X elements are states, right? So X is a state. It's just a real number, and this is a proposition, and you can check this proposition simply but by infinite time by checking the first, the second, the third element, blah 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 blah. Right? As long as you know that the guy is positive, at some point you see some non-zero number in the sequence of the x. Right? So if it happens, you can check it infinite time. It does not decide it; it just checks it. Right? But this guy is bad. It is not open and it's not a proposition because I cannot check it. If something is equal to 0, then if I want to check it, I have to check all the possible elements and make sure that everything is 0, and that is just beyond us, right? So the intuition then is that you use opens. Open means do it in finite time somehow. If it is true, then check it in finite. Okay. What else should I say? I guess that's enough for our truth value. And then now I have to go to my, no, I have to say another thing. Two other things, probably. One is that sometimes people just construct new Heyting algebras from the previous one by some sort of quotient. So let's say that H is a complete Heyting algebra that we had. And then you have a filter. Filter means a subset of H, offset actually, and closed under conjunction, right? So that's a filter. And then you do the quotient over the filter. So meaning that your new H is just, so first define the following equivalence relation on H. So you say that A and B are equivalent if and only, okay, that's not good. If this, which is just the abbreviation of this, is in your filter, and then you prove that this is an equivalence relation. That's easy, using the property of a filter. And then you say that H over F is just H over this equivalence relation. Simply what I'm saying is that you change the notion of truth from one to a filter. You say that whatever is in the filter is true, not just one. And then this property simply is that something is true, then anything bigger than that should be true. And if two things are true, then the conjunction should be true. And then here I'm saying that two things are equivalent if their equivalence is true, right? It is in F. And then I do the quotient over that. So this is the canonical way to make a filter to true, right? I'm collapsing the whole F to 1 in a new one. And that is also Heyting algebra. And the other is that, is it possible to go from a Heyting algebra to a Boolean algebra? We all know that as logicians. But probably I have to say that if I have H as a Heyting algebra, then you can define H double negation, if you like, as the set of all elements such that they are equal to their double negation. And that guy is not just a Heyting algebra, it's a Boolean algebra with the same order, same everything, right? So that's somehow the double negation translation, or the canonical way to make intuitionistic values into classical. Okay. So if you apply this double negation thing here, then you work with some offsets such that they are closed under double negation, meaning that, should I explain it now? No, who cares? Later I will explain. But the double negation stable opens are called usually regular opens, right? If you restrict your opens to regular opens, then you get the regular open simply is some open such that the interior of U bar is U itself. That is equivalent to what I said there. And then these guys, if you restrict all opens to these opens, then the good news is that now you have a Boolean algebra. So everything has the complement, but doesn't matter. So these are about the basic things about my truth values, if you like. And so any question about the truth values? Okay. I guess this means that okay.
Sorry, why are you talking about truth values now? You mean the same thing as Heyting-valued?
You fix one complete Heyting algebra, say. Any element there, I call it the truth value. Right? So now after choosing the new set of truth values, what I want to do is to work with new sets, right? So fix H from now on, it is just fixed. Sometimes in examples I change it, but you don't change H in the whole setting. It is just CHA, complete Heyting algebra. And then define, sometimes people call this H omega. They work with omega and omega set. I call it H set simply because I reserve my omega for sub-object classifier. There's actually no difference. That there is a reason to choose omega because omega somehow has the property of sub-object classifier. But I guess that's better to have different notation for things. So what is H set? H set, you have to think of it as a set with values living inside H, right? It's just a set A and a relation, binary relation. It's not a relation, it's a function R. Function from what to what? From A times A to H, right? So that is your equality. Sometimes people write this, but that would be kind of hard to work with, right? Therefore, I write just R. But that is your equality. An equality of two things should have the value inside your H, the truth value, right? But it is not anything. It has some function with the following two properties. One, of course, you want your equality to be, say, symmetric. This simply means that this means implication, right, between values. So simply I'm saying that if A is equal to B, then B is equal also to A. So therefore it is symmetry of equality. And also you have transitivity of equality, which simply says that if A equals to B and B equals to C, then A equals to C, of course. And you expect reflexivity maybe, right? That maybe the first one should be RAA equals to 1, right? Because everything equals to itself. But it is missing. And I have to explain why. But first, H set is simply a set, any set, with a function like this, with these two properties, right? That is called one H set. Okay, so what happens then to RAA? Because we expect this guy to be 1, but it isn't.
Because it looks like transitivity if you take truth values from H.
Yes, and if you read R as equality.
But it is not in fact transitivity at all. No, because R is the relation function.
Yes. So you expect this, right, to be 1. So any A equals to A, but that's not true, and that's bad. But the reason is this. So that guy is called E of A, the extent of A. So I'm simply assuming that not all the elements inside A really exist, right? They exist in different, you know, with different values, with different extents. And this guy simply captures the extent to which A exists. And if you like, maybe that's better to read this guy. That is the value of A equals B by definition. And this guy is kind of the value that A lives in A, right? And it is not something, technical. It's really important, and we will see it in some examples that it plays a serious role. So it's not just some problem with the setting. Okay, so some examples now, I'm sure, help with the Heyting algebras that we had before, and now we can use them to do we now. So I have to introduce some H sets. The easiest obvious one is that whenever you set H as just the Heyting value or Boolean algebra 0 less than 1, right? Just the usual one. Of course, any set is a set. Simply you write A R and you define A B as if they are equal 1, otherwise 0. That's just the usual notion of set. But you can have more. And that more thing, probably the easiest one is this. So let's say that H is just the power, should be power set of n, say, of natural numbers. It's a Boolean algebra, even. And then set your A as some x, set x to n. So this is just a set of all sequences of x, right? You don't work with one set, you work with a sequence of elements of the set. You change things, right? And then if you work with these guys, then R would be what? R of 2 alpha and beta. To what extent two sequences are equal? The natural thing to say is that just pick all the ends where the guys are equal, really, right? That is the value. That's a natural value, right, over sequences. So people use this thing in, say, so that's just a fancy version of ultra power, kind of. Right. Right. Yes. This one, the extent of, so they call it global. So then the extent of everything is 1, really. Exactly. As some set 2n. No. It should not be, right? A is just a set. These are the values. The values are just subsets of n. The value of equality between two sequences as the points where they are really equal. This is a subset of n. Because R of two things should live inside H, and they live, right? Of course, you can change it to x1, x2, x, etc. That would be some sort of ultra product. That's not really ultra product because you have to do also something else, but doesn't matter. The other is this, probably a bit, I don't know, complex in some sense. So let's say that H is just the opens of some topological space, and A is the set of all functions. Okay, maybe that's better to write. Okay, just to specify the domain of the function, I would write U and F such that U is a open of X and F is a continuous function from U to R. Right? So that is my set. So So U simply is there just to say that I am the domain, right? To have some well-defined domain, but doesn't matter. So you have just some partial functions, not on the whole X, but on some open, right? To R. That's the usual thing, arithmetical thing that open subset of X. And so then what is the extent to which two functions, or if you like, UF and VG, so you have a function on U, you have a function on V, and to what extent they are equal? The natural definition is just the union of all opens, subset of the intersection, such that F restricted to W, because F is defined over U, W is less than U, so you can restrict it, and the restriction G are equal, right? The biggest possible open where F and G are equal. Of course, that is the extent of the equality between F and G, and this guy is inside O of X, because it is just the union of some opens, right? So what I'm saying is that you see the usual thing works with sets, works fine with sets. Two things in set theory are equal or not. But when you work with things that vary, function, sequences, of course you have to change your notion of truth value. Because the simple truth value here simply is that either two sequences are equal or not, but that's not refined enough to work with, right? It doesn't see all the data there, the change of the things, right? And the same here.
So the last case, what if you just put it's a set of things where F and G are equal and defined?
That is not necessarily, actually they are the same, I guess. No, they're not the same. The point is that I want it to be open, right?
Yeah.
That set is not open necessarily
Uh,
because it is just the set of x's such that fx equals to g of x. But I want it to be open. So the biggest open, because it is just let's say that I'm in geometry, we emphasize on opens. I guess. Okay. So, but if you want to work with any, probably I have to go there, but let's not do it. And here in this example, you see that extend thing, right? So what is E of some U F? It is the biggest set where F equals to itself, right? And this is just U, right? It is U, which is some open, but not necessarily X, the whole thing. Simply, I'm saying that with that condition, that extent could be something different from one. I'm simply saying that here I can work with partial functions, not just total functions. And that is kind of important in sheaf theory, therefore, you have it. But if you want some logical example, maybe I can write one for the extent of things, and that keeps historic. So let's say that P and its order is simply this tree. Let's say easier. It is this tree, this, and one branch, right? That's the order and it's P, right? And this is my notion of time, and therefore, as we saw before, H would be just the offsets of P with this, and A is just two elements, say AB, with the following property. What is the following property? The property is this. So here you think that's just the intuitive explanation, right? Here everything is missing. There's no A, no B, right? This is the first point of time. We didn't create anything. Then we go here. Let's say that we create A and B at the same time. or if you like, we discovered them for the first time. And then here they are not equal. And here they are equal. So what's the intuition here? The intuition is that when you go there, you discover equality between the two. Let's say that these are just two big algebraic expressions that you don't know they are equal or not. And here you don't know it, or they are not simply in that word, right? So if you have that interpretation, then to capture the situation via these 8 sets, you say that what is R of, say, A and A? That is the extent of A, right? The points where A is defined or created. So it is just this set, right? So if it is P, Q, R, S, it should be Q, R, S, right? And what is RBB? It's the same. What is RAB? It is different. It is this guy, R, right? This is the point where the A and B are equal, really, right? And we can check that has all the properties that it should, right? So that is some sort of first order Kripke model that you have things and the domain changes, and also you get new equalities. That's just the usual notion of Kripke model or first order style reasoning in intuitions.
Sorry, I forgot something maybe. So to say two things are equal, you have the point where you've got R equals R.
Yes, because at R they are equal. You actually don't do that now.
So
We will later, but now, not now. But if you want, then it should be not now, not.
I was imagining the background
Yeah.
relation R, but you're saying it's not.
No. Kinda, it encodes the relation R, but not. It is more. No, you cannot just. No. It doesn't mean that you can just describe everything based on R. It's more than that. So R is based on that, but not the other way around.
Once you get an element, it should be the bound.
Yes.
And then you also have some facts about the elements. This is how it plays.
Yes, but also equality preserves over time, but not equality not, right?
And being unequal isn't quite a fact yet, because you haven't introduced a notation for it.
Yes. Or not really, because that's just something seriously intuitive, right? Or if you know Kripke model, then it is something independent. I'm transforming any Kripke model into H set. So okay. So also there are some examples for any H. So these are some H's that I chose simply because I wanted to convey the idea, right? But if you have some H, any H, and any set A, you can define the obvious R. What is the obvious R? The obvious R simply is that you read two things. If they are equal, 1, otherwise 0. You have both of these guys in any H, right? Not just in 0, 1. So you can. So these are the classical H sets, if you like, just the sets as H sets. And the other one is that, so this is one. Let's say, just to play with it, let's say that I pick some element in H. Then you can write some set, singleton set, and R, and define R and R star star. This is the only thing that I can define, right? As this U. And it has that property simply because what is the property? R star star should imply R star star. u implies u, and u is less than u. So what I'm saying is that simply for any value, I can construct a singleton. That singleton exists and the extent to which is just u. So I can play with the notion like this. And then the last thing, maybe the cutest of all, is H and Heyting equivalent, right? Because what? Because this guy should be something. So this is binary, right? It's a relation. So let's write it R. And R should go for like H to H, right? It should be a function like this. And just simply define RAB as A B. Because implication is just some binary operator or an H, right? So you define this. Simply I'm saying that use H, use the values themselves, and then this simply means that the values are equivalent. This should be another one, and we see that it is simply because A implies B and B implies C is less than A implies C, etc. Right? Okay. What should I do? The next thing that I have to say is because remember, we want to define a topos, right? That's called the Heyting-valued sets, and Heyting is just some fixed H. So actually, we are defining a category of H sets, right? The category of H sets. These are objects. H sets are objects. So please move me here. And so, what are morphisms? What is a map between two H sets? Let's say that I have A, R, and I have B, S, two different sets, two equalities according to H. And what should be a map between them, you think? What is the natural map between two things? Any function?
No, it's like if something has some value. If like if two things have some value in H, we are then if we use the morphism, then those.
I see. So you are saying that first it should be a function from A to B, respecting R and S, meaning that if two things equal according to R, so you are saying something like this, that the definition should be whatever it is, it should be this, but not any function. It must respect equality, meaning that R A B should be less than S F A S F B, right? Meaning that this equality implies that. So the same suggestion. That's a very good one, but actually it's not the one that we want. And I will explain the relationship between the two later. But what I want is more set theoretical. So if we are in set theory, which means that these R and S are just the trivial ones, then what is the function from A to B? It's a relation, functional relation, right? It is first a function from A times B to 0, 1 with some properties. Because any relation is a function from A times B to 0, right? So if you change 0, 1 to H, you have to change it also here. So therefore, F should be something like this. F must be a relation in quotation, some H relation. And what is H relation? It should be just a map from this to H, such that it is functional, right? So what does it mean to be a functional? So first, because we work with some problematic situation here. The problematic situation is that first, not everything exists. Two, equality is something non-trivial. So we have to respect these things. So therefore, I would say that the obvious thing is that F is, say, well defined. meaning that it respects existence and equality. So, meaning that for existence, it simply means that if two things are related, then they should exist. So therefore, the relation is somehow on the existing parts. So here it means that RAA, or if you like EA, with respect to the first guy, and SBB or EB. So that thing is kind of vague, simply because you have to know which H set you are using. But if you want to be more precise, it should be A index R, B index S. I use E just to simplify, right? So I'm simply saying that if two things are related, then the first exists, the second exists, right? The relation is on the existing part. The second thing is that the F respects equality, meaning that if A1 and A2 are equal, and B1 and B2 are equal, and F of A1 and B1 you have, then you reach F of A2, B2, right? That is simply the fancy way of writing, like if A1 equals to A2 and B1 equals to B2 and F, then you have F of the others. This is just usually true in first order. We don't say it because we assume that equality respects everything. Everything respects equality, but simply it's not the case here because you change your equality, you have to say it out loud. So that's just a basic thing. F is well defined. But now we have to work with the real conditions. The real conditions are one, F is functional. It should be a function, not all relations are functions. And the second is that F should be total, right? So second, F in quotation, probably I have to also put some quotation here somehow. F is what? Is functional. So functional means what? Means functionals mean that if A goes to B1 and also A goes to B2, then the two guys must be equal. That's functional, right? It's functional. It's relation, but not all relations are functional, right? Right? That's the natural thing to have. So the image of one thing should be just unique. And the last thing is that F is, in quotation again, total. Because not all functional relations are total. So the definition simply is that if A exists, or if you like PA, if exists, then it goes to something right? And for the first time, you see that I need this guy. This is my existence. So that is just the fancy way to write that if A exists, then there exists B such that FAB, right? For the existence, I write just the big joint, right? H is complete, therefore I can write it. So I assume that H is complete to just mimic the quantifiers. And later we also need universal quantifier, okay? But also conjunction is always needed to write things, right? Because the main idea is what? You think H-valued style, you rewrite whatever you have in the usual set theory in the new setting as some conditions, something that should be true. And then, of course, you use the usual linguistic structure like conjunction, disjunction, etc., to write it down, right? So that's the point. Yes.
So
Yes. Yes. That's a very good question. So I can do equivalently this. So first you have to, this is in first order, it is like this, right? That is like this.
That meant to be an entail.
Yes. No.
I don't.
The difference is that first you have to bring this guy here to write this. Implies there exists P, right? The equivalent version here would be this. The entailment is this, right? That some proposition implies some proposition, but this is some fact that you say about propositions. The implication between the two is a proposition itself. It's not on the meta level, right? So you write A implies B in two ways, right? In the usual language. You say that A implies B, or you say that A implies B is true. There are two ways to write it down. And I'm saying that this inequality is that guy. To have this guy, so my point is that first I have to bring everything in one side to make it one proposition and then use quantifier over that, right? So then this is that, right? And now you want for all AB, right? You can write this down. And I can do the same. So I can say simply that big and over all AB, both of them. B, oh, yeah, sorry. Yes, A, just A. And also A here. My way around. One. You can write this down. They are equivalent. Because how to prove the equivalence here between this and that is just the usual rules of intuitionistic logic. And all of them are valid simply because we write it down in that way. Therefore, they are equivalent. Really. So there's no difference. But that's a good one. Okay. So, but yeah, yes. So all the conditions, if you have, then you have a morphism. You have H function, if you like. H sets and H function. Okay, that's good. But then what? Then, the good news is that you can transform any function like that you introduced into a map like mine, right? Let's say, let's come back here. Let's say that you have some f with this property, right? Then I can assign capital F, the relation to it. The relation should be what? So the relation, let's say assigned to F, is that FAB is what? A is related to B via the function F. In the usual setting, we write what? If you have function F, we define this relation as equality between F of A and B, right? If I have a function and you want to define the relation that defines the function really, you say that A and B are related when F of the first equals to the second, right? The same is here. So I have equality. So S FAB. But also I have to add something, and that something is that A exists. Because I want my function to be on the existing parts. That's just the twist of it, but right? But simply I'm saying that yes, they are related when f of a equals to b. And then you can check that actually you have all the properties here via this definition, right? So for instance, it is well defined simply because, of course, E of A is here, therefore it implies the existence of A, but it also implies the existence of B. And how do I know that? By this. Because RAA implies S f of A, right? And therefore, S of f of A is provable with this, and therefore S of B is provable because B and f of A equal, right? And then you can check millions of the others, right? Like the last one, the totality would be like what? So if I have E of A, then I have to prove the disjunction on all B's f of AB. And of course, I choose that B as f of A, small f of A, and then I have f of A, simply because, yes, that is just S f A and E of A. E of A comes from this guy, and E of A also implies that f of B equals to f of B. So it's just, complex playing with these things, but you can just check all of them and you see that that is actually a function. Okay. So, okay, these are my morphisms. And so to have a category of H sets, of course, I need identity. One morphism as identity and composition of identities. So what is the identity? How to define identity? You have to think relationally, right? So what's the relation of identity? The usual is just R, exactly. Because this should be a function from A times A to H, and of course it should be R, right? Because simply I'm saying that this must be equal to that, and equality with respect to which relation? R, of course, right? That's R. Of course, then you have to check, you have to all the things, right? So the first is that RAA implies the rest, simply use just transitivity, blah, blah. And, or if you like, I don't know which one I have to check. So say, yeah, everything is easy, just check them. But you have to check all the conditions to make sure that it is just real morphism. But it is easy. And what is composition then? So let's say that you go with F to this. Sorry. And with G, you go to, say, C and T. So then what is composition of G, O, F? It should be a relation, of course, in the new sense of the word. So you have to define this. And what should be the definition of G, O, F of, say, AC? Exactly on B, right? Simply you say that something is related to something if there exists something here such that you have this and you have that. So there exists some B such that f of A and B and G of BC. That should be the natural definition of composition. Of course, you have to prove that this composition is associative, and also that guy is real identity of this. That is easy. The only thing that I want to prove maybe is just that, say, G O identity is G. So let's say, because these are two functions, so let's just apply this guy onto some AC. It is simply what? B, but B is in A, because these two are equal, right? That's identity. And what? And F is identity, so therefore it is R, RAB, and GBC. And you want to show that this is equal to what? To G itself, right? So how do I know this equality? Really? I have to prove two inequalities. This implies that. Simply just pick this B as A. So you have GAC implies GAC and RAA. How? RAA is not true always, but G is well defined, right? Therefore, G of anything implies the existence of A. And the other, you have big disjunction, you have to prove that each of these guys is less than GAC. So then.
Can you move the
E-
camera, please?
Now it doesn't work. Yes. Yeah. So I'm just proving that G equals to GO identity. So, and we are here. So we want to prove that this equality. I prove that this is less than this guy. Now I have to prove that this guy is less than GAC. So it's just big disjunction. Each of these guys should be less than GAC. And you know it because B goes to C and G respects equality. And this is equality between A and B. Therefore, you have GAC. So you play with all the conditions and you prove things. That's the point. So all the things, if you check millions of things, and then you actually prove that now you have a category, the category of H sets. So simply I'm changing the category set to category H set by changing the values from 0, 1 to H and to mimic whatever I know of set theory, say. So we have the category of H sets, right? Perfect. Heyting-valued set. So the next task is just to show that this category that I write H set simply, right, like set, is a topos. And to prove, I need to check something. So first, I need to check finite limits, right?
Sorry, you just said the H set again, it's given by this A, where A is a set,
Yes.
not a class.
No. A is a set, and R is that relation. And that's it. Yes. So how do I know that I have finite limits? I have to check some basic finite limits, like, I don't know, binary product and equalizer, for instance. But just because it is useful and we need to know these things, probably it's good to start with the obvious one, which is just a terminal object. You remember that terminal object in a category is some object 1, such that from any other object, you get just unique morphism to it, right? So what is 1 in H sets? In sets, it is a singleton. It doesn't matter which one. I usually write singleton star. And probably it's the same here, but also you need some relation, some equality relation. Why not just the obvious equality relation, right? So write just the star and define R. Say this is my 1. R1 is, so you have to define this guy, right? Simply. And define it as 1. It is just the usual set, pretending that it is an H set. And so how do I know that it is terminal? So from any AR, there must be one unique morphism in that sense to this guy. One way is just to use that trick, because if you have a function, then you can construct something from that and use just the constant function. And the only thing that you have to prove is that that function respects R, but it respects it simply because 1 is bigger than anything. So let's just use it. But to prove the uniqueness, probably it's better to work with this f. And first, let's define f. So what, or let's discover f. Because I want to say that f is unique. F should be something, and that something works. So what is f? Whatever f is, you have to define something of this sort for any a, right? Okay, perfect. And what I'm saying is that you have to define it as R star star. That is the only way to do it. No, sorry, RAA. RAA. The extent to which A exists. So you have to simply because whatever f is, f of something implies the existence of A. So you have this. And also you have that because it says this is totality. If A exists, then there should be some element, and there is just one element, star, such that A goes to that star. So these two guys are equal. There is no other way. So this is uniqueness. But also you have to prove that really this guy with this definition is a morphism, but this is easy, or it is equivalent to what we had there. Okay, so that's terminal. And what if I have two things? And what is the product of these two guys? It should be A times B. And probably that's fair to write R times S. So what does it mean? It means that this is a relation over this guy, meaning that it goes from A times B times A times B, twice of this guy, to H. And then you have A1, B1, A2, B2, and then that should be just simply R of A1, A2 conjunction with B of B2. Simply, I'm saying that the equality between two elements here is the equality of the first and the equality of the second. That's it. You have to check that this is really an H set by this definition, but it is, come on. And the other thing that we need for product is what? Is just the projections. And what are the projections? Just trivial. So the projection is as it should be. What is the projection? A projection, say P0, must go from this guy, A times B, and R times S to AR, say, to the first one. And what is by definition P0? P0 is a function from HB times A to H. And what is the value? So if you read A, B, and A prime, projection simply says that if you have a pair and something else, they are in relation when this is just the A part of that, right? So not just say it. So that must go to R A prime. And the same for B. And then you have to prove that it's a morphism. You have to also, from any C, probably this is the only time that I really write it. So maybe I have to. So let's say that I have CT. And I go to some F to AR. And also I go from CT to some BS with some G. And then, of course, you need some H, right? It should be unique from CT to the time, the product of these two, right? The problem is that, okay, you have to prove that H exists, you have to prove that H is unique, but just the definition of H probably helps. So H, whatever, H is a bad name, sorry, but whatever. So you have to define a function from C times A times B. This is why it's bad, right? And how to define it? Simply, it says that send CAB to what? So what's the relation? C must go to A via F and to B via G, right? So therefore, it should be F A C, no, CA and G CB, right? And millions of the other things that you have to do. But then you have all products, all finite products, if you like. Also, you have equalizers. I also explain the equalizer simply because it says something about the existence, and that's good. But then probably the others I have to just mention and say some basic things about them. I'm sure that I don't have time for that. But anyway, equalize. So what if I have A, R, F, G to BS, right? And I want something here and some map here such that they equalizes, it equalizes F and G. So the usual trick is what? You pick a subset of A where F and G are equal, in set theory. And I want to do the same kind of here. But the point is that now I can change the extent to which something exists. Therefore, I can simply use A again with the new R and define, so maybe define existence of some A here to what? To existence of it and equality between F and G on that A, meaning there exists some B in B such that F goes to B and G also goes to the same B. Yes, right? So I'm saying that the image are equal. So therefore, E exists. A exists here. And then what is the equality? Equality is simply R prime between A and B, means that, of course, they should exist in small one. So that's bad name, sorry, A prime. And they must equal with respect to A. So everything is a bit harder simply because you have to deal also with the existence property and equality. It's simply something like what's called the existence logic. There's something called existence logic that I guess it's called existence logic, such that it's not like that every term that you write exists. You also have some exist predicate, and sometimes you the rules are something like if say t exists, then you can say and you have a of t, then you can say there exists x a of x. It is something like that, right? This is somehow the semantics of that kind of logic that I forgot its name. So yes, therefore you have equalizers. You have to, of course, show, oh, no, that is just this guy. You also need the morphism. The morphism is easy, simply just this guy and that guy equals with respect to R, and also one is inside that one. It's just inclusion, right? So inclusion, the relation of inclusion is just equality. And then you have to show that the composition, with that definition of composition, they are equal, 1. 2, this is the best one, meaning that if you have another one, then you can factor it. But I don't do that, of course. And then just believe me that you can construct everything relatively natural. So, and we don't have time, I guess. Probably that's good just to mention the last one that I can, which is just the exponentiation. And because what are the axioms? You need finite limit, you need exponential object, you need a sub-object classifier, right? So let me just mention how to construct the exponential. And because I don't want to explain everything, let's say that I have some BS and some AR, and this should be some H set storing all maps, right, somehow. So what is it? It's a pair. And the idea is simple. So here you have all possible relations, and relation here means H2 A times B. All the functions from A times B to H. And then probably some name here, T. So what is T? So one, maybe that's something about the practice. Working with H sets, practice is that usually you define first the existence and then the equality, assuming that you have the existence. That is psychologically easier, right? Because then you know your domain. And so here, for instance, what is E? E of something here. What is something here? It is, say, some function f. F is a function from A times B to H. What should be the extent of it? It should be the value of F being a morphism, because it is just a relation. So it is just this value. Let's say F is a morphism. What do I mean by that? So simply, it is just a conjunction of those things. F is well defined. F is respecting equality. F is total. F is functional, right? For instance, so it should be just conjunction between four things, right? For instance, the first, just write down one. So what is the first? The first simply says that, so this one says that F should be well defined. Okay, let's write it down. So what is well defined? Meaning that for any A and B, F of AB must imply RAA and SBB, right? That is the value, right? That is the condition. For any AB, you have to have this. That's the value of it, right? And you can see that I need big for all or conjunction. Also, I need implication, right? To internalize things, to say that that is just, this is less than that for any A and B. You want to make it into one value, not one statement. And this is the value corresponding to it, right? So you put it here, you put the next there, there. And one, if you remember, was suggested by Neil, the last one, how to write this down. It was like this. You put this guy without one as the value. So simply, I'm saying that E of F says F is a morphism. And what is equality? Equality is also easy. So, so let's say the T of F and G. So of course, both of them must exist because each time equality implies existence, always. That's the case. So therefore, yes. And when two functions are equal, what is the value of equality of two functions? They should be equal for any A and B. So the value is that for any AB, right, F AB is equivalent to G AB, right? Of course. That is the exponentiation. Simply, I have all the functions, more than that, but the extent just captures it, and just the equality between functions. And then, of course, you need a morphism. The morphism, the evaluation morphism, must go from this to that. Equivalently, it means that you need a function from this times A times B to H, and that is just the evaluation function, of course. And then you have to prove that that is just a morphism and everything is just universal, therefore you have exponentiation. I won't do that, of course, but you have it, right? So you have exponentiation, and then finally, next time, we will see the subobject classifier, and therefore that guy is a topos, and we will see how it's related to the other construction that we had. But the last thing that I have to say is that it is just a big mess, right? Working with this or that. The essence is this, that you know that your values must have some structures like these things, because you want to express these things that you have already in sets. Now you have it here. So for that, of course, you need implication to internalize those things inside. You need conjunction, disjunction, but the main thing is that you need these big two for all, and they exist, right? But if you think about it, maybe you can say that maybe we don't need a universal value set. We need somehow to know how to deal with the Heyting structure plus quantifiers, not like this, right? And as long as we have some machine to do that, we can do the same game, because the game is not really, in some sense, it is independent of H being H, right? Being a Heyting algebra. You have to have some structure, but we now say that everything is universally coming from one H, but probably it can come from, different H's, if you like. And that is a serious, crucial notion. that I will talk about it later, I guess, a bit. So I guess that's it for now. Thanks. Probably I have to say something that this is 8 Heyting value, right? Of course, you can pick Heyting as some Boolean algebra, right? Because it's just more general. And then that would be just the usual Boolean valued models that people talk about in forcing and set theory, right? When you construct Boolean valued models, either in set theory or in arithmetic or whatever, simply you do this, right? You pick one complete Boolean algebra and you construct, there are different settings, but you either construct the whole category of all H sets or just one H set as some new structure where you want to interpret things, right? So that is just the categorical flavor of, say, Boolean valued model theory. If your Heyting algebra is Boolean. So, that's a good question. So if you just care about classical mathematics, then of course your model should be classical. So then there's no reason. Just work with Booleans. 1, 2. However,
For this forcing, for this independence.
yes, because it is classical independence. If you want some intuitionistic independence, which is important, not made up, then of course you need Heyting algebras. This is one thing. But the other is that when you have the theory for Heyting algebras, as we will see next time, it is more natural to compare it with other constructions, right? Being Boolean is something that you add and you have to carry all the time. Of course, in applications you need it. But working with Heyting algebra is somehow canonical construction that you need. Think about this, that the different versions of constructing topoi that we had for now just 2 examples, naturally they are intuitionistic, but you have to make them somehow by shrinking or doing some tricks intuitionistic, classical, sorry. So if you work intuitionistically, everything is more smooth, more canonical, more universal. You see what is the ingredients, etc. And whenever you want, you can land. That's actually my trick. So I want to explain this, say 8 sets. And then at the end of the 8 set story, maybe next time, I want to explain the essence of Cohen forcing. And then you see that you need Booleanness. And there I add Booleanness just by one trick, right? And you see that, okay, Booleanness is not the main ingredient of the construction. The main ingredient is somewhere else. Just forget about it, the dense or whatever thing that usually people do in forcing. It is just something that you have to carry. It messes with the image. The image is just more clean and also universal. So in some sense, it is just the best way to do something. So you can see it. Sure.
H sets to be a tuple of set in a relation instead of class and a relation such that from each perspective of proof value, this class is a set.
That's a size issue, right? So I'm not sure that I understand.
Taking the drawing and meter.
That's true. So then I have a problem here, but I'm not sure that the question is about them. So yes, I assume that they are sets, but you are asking that if I change it to classes, then can I do the same things or?
Class such that for each truth value, when we prove this truth value or weaker, then the existence.
I see.
Elements form a set.
I see. So you put some bounds there somehow to yes, I guess so. I guess one should check, but I guess everything, yeah, as long as you can just harness these guys, then that should be fine, I guess. This is one thing. The other is that sometimes people just simply go for bigger notion of set, by universes, That's the usual trick here. It's not the usual trick in forcing, but you go for a big universe that kills somehow the idea of forcing somehow. But then your classes are small in the big universe. For the forcing argument, that's not good. The other is it is possible also to work with somehow classes with really values, and that's called class forcing, kind of, or class. But not that's the thing, that you don't have all the structure, but you can just somehow harness something like that with different tricks to construct the thing. There are many ways to bring in the classes, I would say. Not really, because what I want to do, my main task is not forcing, is just constructing toposes, right? That is just a natural way to construct the toposes, right? Because of the size issues again, because my toposes are locally small, but
How come you're allowed to do these big conjunctions?
Yes, because I said that whenever you have a Heyting algebra which is complete, these guys also exist. So if big join exists, then big meet also exists. That's some easy theorem in lattices. So then, yes, I'm allowed.
In forcing, usually people define enforcing condition, which is boundary over sets, and forcing is then defined a lot like forcing in critical model.
Exactly.
So is it the connection that you would get from partial algebra?
Yes. The thing is that so first people use that, right? Also, people use Boolean valued models, and they know that they are kind of equivalent, right? But that kind of equivalent is real equivalence here. The real equivalent is actually this, that next time I will prove that if you have, that's kind of a very beautiful theorem that connects geometry somehow to logic. So for any H, the category of H sets is equivalent to the category of sheaves over H, right? So read H as some topological space, opens of a topological space if you like. Then you have sheaves over it, as we had before. And then this category is just the same as this category. So, but here, the idea is that you vary over something. And if your something, meaning the H, is just the opposites of some P, as we had before, then this Boolean version, you assign opposites. But here, you really have functions that vary over P's, over conditions. So they are kind of the same thing. So you can also present things in this way or in that way. And my plan is just to show this first, then explain the main idea via H sets, because it is more logical, canonical, we can see it. But later I come back to sheaves, and I really try to prove things via sheaves. This is one thing. Maybe now it's time to say something, and that something is that people usually like this Boolean valued or Heyting-valued models simply because they are easier than sheaves, right? They are just, we have just the usual set plus some new equality. That's easier, more, natural to work with. Then you may ask that what is then the deal with sheaves, right? So just forget the whole sheaf theory, and whenever you want to present these independence things, work here. The problem is that H sets can simply capture these type of sheaves, the Grothendieck toposes, over a Heyting algebra, a complete Heyting algebra, over, let's say that you had this set to the C thing, right? And later the sheaves. So if your C is a poset, you can see it like this. If it is not a poset, then you need the real sheaf theory. And logically, we can see later that always axiom of choice is true in these two. So if you want to refute axiom of choice via some notion of valued models of forcing, you are forced to go for full scale Grothendieck toposes for full scale sheaves. So it doesn't work. So you cannot leave here. In set theory, people don't do that. So because that's the universal version, people just do the tricks. So they construct models like this, then they shrink the model. And yes, they add that symmetry and then restrict to the symmetric part, etc. Yes, which is kind of, and that direct proof is kind of natural, that you can see that, of course, you have to universally add this. Why not, right? So the conceptually, it's better, I would say. Right? Next time.